Hey class, we are looking at our last lesson from chapter 15. There's actually one lesson after this in the book on regular polyhedra, and it's really just definitions of regular polyhedra. That one's a really easy one because if we remember regular polygons, okay, regular polygons were 2D. And remember we said that irregular polygons would have the same sides and the same angles. They were equilateral and equiangular. Regular polyhedra, polyhedra would be the plural. Polyhedron would be one, or polyhedra. Okay, that's the plural. They are 3D. Okay, so these are three-dimensional solids that will have the same shape on every side. Okay, so regular polygons would have the same angles all around and the same length of sides all around, so they're equilateral and equiangular. Regular polyhedra mean they have the same shapes on every side. So imagine if you had a pyramid with an equilateral triangle as its base instead of a square as its base. There are actually very few figures that you can make that are regular polyhedron. Because you think like a soccer ball, you have to have a combination of pentagons and hexagons to make it form into that soccer ball shape. So there's very, very few regular polyhedrons. And you can look at pictures of those in the book. I'm not even going to attempt to draw them here because drawing in 3D is hard. Okay. But today we're going to talk about similar solids. And if we think back to chapter 10, which was our chapter on similar figures, we actually already talked about this, but we're going to talk about it again here. We talked about kind of the ratios of similarity. That if I had, for example, a square, okay, the squares are easy. Okay, if I have a square and each side of the square was 2, okay, and then I had a similar square whose sides are twice as large. So instead of 2, this one is 4 and 4. So its sides are twice as large. So the perimeter of this square, okay, perimeter, we're just adding up the sides. So the perimeter is going to be 8. The perimeter of this one, 4 plus 4 plus 4 plus 4. The perimeter is going to be 16. Okay. But the area of this one, okay, and so we see our perimeter here is twice the perimeter of the smaller one, and the sides are twice as big as the sides here. But if you remember back to chapter 10, the area is not going to be twice as big. So the area here, 2 times 2, gives us an area of 4. But the area here, 4 times 4, gives us an area of 16. Okay? So when we compare 16 and 4, this area is 4 times as big as this area. Okay? So the perimeter is twice as big, just like the side lengths are twice as long. But the area is 4 times as big. So that's where we said that the ratio between the sides in similar figures is going to be the same as the ratio of the perimeters, but the area is actually going to be the square of that. So same thing, if this had been instead 3 for the sides of the small one, and we made this one, say 3, let's say we made it 9. Okay, so now it's 3 times as big. Okay, so the perimeter, 3 times 4, that's going to be 12. The perimeter here, 9 times 4, that's going to be 36. So my sides This one has sides that are 3 times as long as this one. Its perimeter is 3 times as big as this one. But my area, 3 times 3, is going to give me 9. But here, my area, 9 times 9 gives me 81. So the area here is 9 times bigger than the area there, even though the perimeter is only 3 times longer. So that ratio between them is 3 to 1. It's 3 times bigger, but the area is 3 squared times bigger. So it's the ratio of the sides of the similar figure squared gives me the ratio of the areas. Okay, so that's what we learned back in chapter 10, that the ratio of the areas is going to be the square of the ratio of the sides in similar figures. But then if you remember, we briefly talked about volume, and that's what we want to look at here since we're now dealing with solids. If you remember, we talked about the volume in terms of like a cake, that when you increase the size of the cake, you are going to massively increase the volume of cake that you have. So I was going to show you some examples of that with some rough cylinders. I know that these glass jars are not going to be exactly cylinders, but they are fairly cylindrical in shape, and then I have this nice big cylinder here. And so we want to compare some dimensions on this, and what dimensions are important when we are comparing figures. Okay, so I've got this little jar here. And what we need to take into account is all of the sides. When I had a square, it's easy because all the sides of the square are the same. Okay, but when I'm talking about a cylinder, if you remember from the first homework assignment you had where you looked at cylinder surface areas and volumes, with cylinder volume, I'm concerned with the area of the circle here and with the height of the cylinder. Okay, so when I have these two, okay, these are not similar figures, right? One is short and squat, and the other is tall. And more importantly, their dimensions aren't the same. Okay, so this one has, a diameter of about 3, okay, roughly 3. This one also has a diameter of about 3. Okay, so their diameters are the same. Now, when we compare their heights, okay, you can see the height here is about 3.5, and the height here is about 6.5. So the height of this one is almost twice the height of this one, but their diameter is the same. So they expanded in one direction, but not in all directions. So we know that they're not similar figures, okay? So we can also see with their volume, okay? It should make sense to us that this one here is going to have about twice the volume of this one here. Because if you just took 2 of these and stacked them on top of each other, okay, so that you have twice the volume, that would be about the same as this one here, right? Okay, we'll even check it with some water, okay? Let's see about this so that we can actually measure the water. Okay, there's about 1 cup. Okay, so there's 1 cup. And two cups. Okay, so this little one holds about 2 cups of water. Okay, so I would expect from looking at these that this big one would then hold about 4 cups of water. Okay, because it looks like this one plus another one on top. Okay, so let's see. 1. Yes, this would go faster if I had an extra hand. is not holding the camera. 2 and a little extra. Okay. There's 2 cups. 3 cups. You literally drank out of my math experiment. Okay. And roughly 4 cups. See, this is what happens when you're filming videos at home. Okay, so the volume we can show here is about twice the volume of this one. Okay, but they're not similar. This doesn't surprise me all that much. Okay, here's the one that I do want to look at. Okay, this one, remember we said was about 3 inches in diameter. Okay, so let's look at this guy. This guy is 6 inches in diameter. Okay, so it is twice the diameter of this little guy. We said that this little guy was about 3.5 inches high, and this guy is 6.5 inches high. So almost twice the height and twice the diameter. So both of the dimensions are doubled, both the diameter and the height, the things that we care about for volume. So these are roughly similar figures. They have twice the diameter and twice the height. Now, if you remember back to chapter 10 when we talked about similar figures there, we said that while the ratio of the perimeters would be the same as the ratio of their dimensions, the ratio of areas would be the square of it. We said that the ratio of the volumes would be the cube of it. Okay, so if this one is twice as big, its surface area should be 2 squared, 4 times as big, but its volume should be 8 times as big. So if this one held 2 cups, this one should hold 16 cups of water. Okay, let's see. This one, remember, had 4. Yep, 4. This was another 2. So that puts us at 6. Okay, we know that this one holds about 4, so let's use that as a rough measuring. Okay, so we were at 6, 4, that's 10. And we know that it's not quite twice as big because it was only 6.5 inches instead of full 7 inches. Okay, so that was another cup there. So we were at 6 plus 4 is 10, 11. Okay, so 11, and I'm now out of water in my pitcher, but we're still not full. But you can see this was 2 cups. This is now at 11 cups with room for at least 2 or 3 more cups. So it's not, even though it's twice the height and twice the diameter, you can see it's not twice the volume like this one that had the same diameter but was twice the height. This one was twice the volume, but this one is much more. Already we've got about 6 times the volume in there, but I think that if we filled it up to the top, we could get that 8 times the volume in there. So remember, our ratio is going to be, you take the ratio of your dimensions, your height, your diameter, whatever those external dimensions are, and you square that to get the ratio of the surface areas, but you cube that to get the ratio of the volumes. Okay? Thanks so much.